In this video, I want to talk about some real important concepts before we go into depth in learning more about the nature of science and how science works and how the universe works. So, I mentioned in my introduction video that one of the problems people have in grasping science concepts is that we often use the English language in science, but with very specific meanings. And so we end up using words that have multiple meanings in common speech or vernacular, but in science we have very specific definitions for them. And we call those operational definitions. When I was in the classroom, one of the first things I would talk to my students about is this concept of operational definitions, because I think a lot of confusion around science is people hear a term used by a scientist, but they define it as if it was their best friend. One of those that we're going to address in this video is the word theory, and I will talk more about it later, but it causes a great deal of confusion between scientifically literate people and people who are not literate in science. So we're going to start with operational definitions. I would like specifically to look at five terms: observation, fact, hypothesis, law, and theory. So we're going to start with, what is an observation? In science, an observation is not just looking at something. It is the systemic and careful gathering of data, information about a natural phenomenon. And it usually involves using tools. It doesn't just mean observing. This really comes to the forefront in the social sciences and sometimes in biology, where you see a scientist simply observing something. So in biology, you may have a scientist who's sitting in the woods observing the behavior of a particular bird or a rabbit. And the layperson says, oh, they're just observing. But what you don't realize is that that scientist is somehow making very specific notes. Nowadays, we usually take a video camera. We video what's going on. We even do that in social sciences. My degree is in curriculum instruction. It's in education. I've conducted research in how students learn science concepts because my degree specifically focused on how people learn science. And we use videos. And then we go through the videos and we actually come up with coding systems so that we can literally count how many times a certain kind of interaction happened in the classroom, so that we can actually document what percentage of the kids were engaged or not engaged. We're not just sitting there observing. Because what we've discovered in science is if you just observe, you tend to see what you want to see. So you have to have some way to document, to collect the information and data. In the physical sciences, it's a lot easier. We tend to use instruments. We measure speed and velocity and temperature and all those different kind of things, and we get numbers. Show me the numbers. And how many decimal places? That determines how precise, how close to the actual data you are. So an observation is not just generally looking at something. It is literally taking time to collect the information. Now we understand that even the most good-intentioned scientists can have bias in their observations. Even using techniques like coding techniques or instrumentation, bias can still cause a problem. We need to talk about bias. It's not one of the words that I started with, but it's an important word in the field of science. Bias is the enemy of scientific thought. In many ways, an understanding of bias was a fundamental breakthrough that paved the way for the development of science. When we talk about the scientific method And we all learned the 5 steps or 6 steps, or I like 7 steps of the scientific method in school. But most scientists go, well, we really don't do things like that. What we kind of miss in all that discussion is that one of the underpinnings of scientific method is an understanding that everybody has biases, and that we need to develop our experiments in such a way to minimize the amount of bias. So we develop our experiments, we develop our data collection in ways that we try to minimize bias, and then we let other people look at it. We publish our work. We let them look at our procedures. We let them look at how we collected the data. Is our data accurate in the way that we collected it? For my doctoral dissertation, I studied how well students learn science concepts in a planetarium setting versus a classroom setting. I had to develop a questionnaire, a test, a quiz to measure students' learning. It had to be validated. We had to run statistical analysis to see if it performed like I claimed it performed. And all of that was published in my dissertation and in my research so that other people could look at it and say, Joel's lost his mind. That quiz is not valid. It really doesn't measure what he's asking. Or they could look at it and say, if a kid scored this on this test, then it shows that they have an understanding of a specific concept. So we realize that we want to be right. And so sometimes it's real easy to not deliberately fudge, but accidentally fudge the data. Sometimes it's deliberate. But most of the time in science, when bias creeps in, it's something that the researcher just missed. They just weren't paying attention. Therefore, they messed up. All right? But we've got to work on controlling bias. And when we take observations, that's one of the ways that we address our bias, is we try to come up with techniques and ways of collecting that data so that we get the truth, not just what we think the truth is. The next operational definition I want to talk to you about is a fact. Facts are the data points. It's what happened. They're the results of direct observations, but they are considered provisional, which means we accept this as a fact until and unless new evidence is discovered. That's the other thing about science is we're never done. We come to conclusions, we collect evidence, we get data, we draw some conclusions, we make some decisions about things, but we're always realize that all it takes sometimes is one piece of evidence to call into question everything that we thought was a fact. So facts are data points. They are provisional until and unless new evidence is accepted. If new evidence doesn't contradict them, then we kind of accept them as they are. The next science term I want to talk about is a hypothesis. And this one gets under my skin. So often I hear teachers and other people say, hypothesis, that's just an educated guess. So I went around and asked a bunch of students, some elementary grade students, I said, what's a hypothesis? And they were good students. They listened in science class, and they said, oh, it's an educated guess. And I'm like, okay, what does that mean? What does it mean that it's an educated guess? And what I heard from them was, well, that's a guess by a scientist. That's a guess by a smart person. And I began to wonder, as a child who is learning about science, and I think a hypothesis is an educated guess, and it's a guess by an educated person or a smart person or someone who's gone to college or a scientist. When they look in the mirror in the morning, do they see themselves as someone who can make a hypothesis? This really came to me in working with students about science fair projects and the difficulty that so many of those students had in coming up with a hypothesis. I think part of the problem is they don't see themselves as a scientist, and therefore if a hypothesis is an educated guess and they're not educated, they can't make a hypothesis. So a better way of looking at a hypothesis, and my way of saying it is, it's the best explanation of the known facts. We've collected some information, we know some things, and we try to come up with some explanation, usually in terms of whether one thing affects another thing. One variable affects another variable, things that can change. Definition you see on the screen, I got off the internet. I don't like going to dictionaries for definitions because dictionaries are descriptive. They tell you how that word is used and what it means in its uses, and that's why in dictionaries you get lots and lots of different definitions that are not always the same. There are some scientific dictionaries that are prescriptive, that try to say this is what scientists mean when they say a hypothesis. And what I have here is a definition from one of those prescriptive dictionaries. And it says it's a testable proposed explanation for a narrow set of events. It serves as a starting point for research and predicts relationships between variables. That's not an exact quote from the technical dictionary, but that's... The technical dictionaries are sometimes very difficult to read and understand because they are technical, so I kind of cleaned it up a little bit. But it's very different than an educated guess. It is not a guess. It's an explanation that can be tested. That's the key. It must be falsifiable. What does that mean? To be a scientific hypothesis, there has to be some way to prove it wrong. If there's no way to prove it wrong, then it's really not a good scientific hypothesis, because how can you test it? An example of an untestable hypothesis would be that there is an invisible, undetectable dragon living in my garage. There's no way to disprove that, because if it's invisible and undetectable, there's no way to test to see if that hypothesis is true or not. Now that's kind of a funny example, but it gets to the idea that scientific hypothesis must be falsifiable. Next term I want to talk about is a law. I have found with many students that they think a law is the highest concept in science, the law of gravity. Actually, that's not true. A law is simply a statement, often expressed mathematically, that describes a fundamental thing that happens, that is observable and can be measured in the natural world. For example, Newton has a law of gravity. Newton's law of gravity says that if you drop an object near the surface of the earth, it will accelerate towards the center of the earth, and its speed will increase at 9.8 meters per second for every second that it falls. It's a mathematical equation. It allows me to imagine scenarios where I drop objects from certain heights, and I can calculate, if they've been falling X number of seconds, how fast they're going to be going. And it works every time. Over and over. It's been tested. Laws are based on multiple observations over time. They've been confirmed by multiple measurements, multiple experience. They are about what happened. They don't explain why it happened. So, Newton's law of gravity does not explain why objects fall. They just are the mathematical model that predicts what an object will be doing after it's fallen for a certain length of time. Now we get to the last one, theory. Probably the most misunderstood scientific term, because in common speech it just means a hunch or a guess. Well, it's just a theory. It always gets to me whenever I hear somebody say that evolution's just a theory. What they don't understand is in science, a theory is the big idea. It is the most powerful thing. in science. A theory explains how some part of the universe works. This is the why. This is why objects fall when released near the surface of the earth. It is backed up with lots of observations and experiments. It's withstood the test of time. It makes predictions that we can test for the future. Theories can be changed, and very often are, with new evidence. But strong evidence is needed to reject a theory completely. So I'll give you an example of the difference between a theory and a law. I talked about Newton's law of gravity. Newton's law of gravity is mathematical prediction. It allows us to predict what happens when an object is released in a gravitational field. His law explains the moon orbiting the earth and the earth orbiting the sun because they all follow the mathematical laws that Isaac Newton proposed. He did that about 350 years ago. But about 100 years ago, Albert Einstein developed gravitational theory. And gravitational theory is the why objects fall. So what Einstein argues in his general relativity is that matter bends space. Actually, he calls it space-time. We're not going to get into all that right now. And that objects near other objects simply travel in straight lines along that bent space-time. That's why objects fall. And that's why the moon orbits. Einstein's theory doesn't just let you predict what the object's going to do when you let go of it. It also explains the why behind it. And one of the crazy things is that we often have laws and theories that have the same name. So we have Newton's law of gravity and we have Einstein's gravitational theory or theory of gravity. One of the topics we will deal with down the line is this concept of evolution. There's a fact of evolution. We've observed it. There's a law that explains how organisms evolved, and then there's a theory of evolution, which is the explanation of the how this phenomenon happens and why this phenomenon happens. So theories are big ideas. So the next time you hear somebody say, well, that's just a theory, if it's in a scientific context, they don't know what a theory is. All right? Hey, when you know, you know. I'm going to be releasing a couple of videos this week. The next one will be an introduction to the atom. And along with that, I'll be producing what's called Science Friday questions. And if you're one of my former students, you know what a Science Friday question is. If not, stick around. You'll find out. I think you'll enjoy them. You have a great day.